Hi everyone, welcome to our video on defining absolute extrema. So absolute extrema is the really just either the largest y value or the smallest y value that is defined in a graph. And if it is on a closed interval, so we kind of have it, I'm just going to kind of underline right there. So that's a closed interval with the brackets. That means that they will always exist. Both of them will exist. All right, so let's show different cases here with the same graph, just on different intervals. So in number one, it wants us to graph this function, y equals 4 minus x squared, on the interval where it's saying no restriction, so on its entire domain. Okay, well, to quickly graph this, it would be up 4 is where the vertex would be. And then after that, it would be a parabola that goes downward. Something like this. Okay, and my pin, let me try that one again. So it's difficult to draw with the computer pin. So it's something like that. Okay, so it doesn't have to be perfect. Okay, so there's our parabola. It is one that opens downward. Okay, so what we have here, because this does go down forever, there is no absolute minimum. Okay, so this it goes down forever. Down forever. So no absolute minimum. Okay, because that means there's no defined y value that's really small. So going down to infinity is not a y coordinate, so that means that there is no smallest y value. However, where it meets at the top here, that the vertex, that is our largest y value. Okay, so we have this point, the 0, 4. So the 0, 4 is the actual point. And with that 0, 4, just the y-coordinate itself would be the absolute maximum. So we have an absolute max of 4 at x equals 0. Okay, and I'm going to box that up. There it is. All right, so it's just this is defined. That's a defined y value, so that's why we have an absolute maximum. It is the biggest one anywhere in this entire graph. It does not have to be at a peak. On this one, it did happen to be at a peak, but it doesn't even have to be at a peak. Okay, so it is just the largest defined y value. All right, so with this one, it says on -1, 2. All right, well, if we were to graph it, and I did that pretty accurately actually on the -1, if we do plug -1 into this function, we would have 4 minus -1 squared, which does become just 3 eventually. So -1, 3, 1, 2, 3 is right here, and it would be a solid dot because we're using a bracket. And then at 2, if I do plug 2 into this, it would be 4 minus 4 is 0, so that would be the x-intercept right there. And then we already know it does have the vertex up top like that. And so from our previous picture, we have just a part of this graph. So our first graph that we did had a domain that was all real numbers. This one, they want it restricted, so it's on a smaller interval. Well, because it is a closed interval, because they use both brackets, that means we will definitely have an absolute maximum and an absolute minimum. So on this problem, where it peaks, right here, right there, is again where we have an absolute maximum. So at 0, 4, the 4 is the important one. So we have absolute max of 4 at x equals 0. So there's the absolute maximum. And our absolute minimum, well, it's the smallest defined y value. So just look as far down as you can, and it happens to be at 2, 0. So our y-coordinate there, that's the smallest, is 0. So we have an absolute minimum of 0 at x equals 2. And there's that. Okay, so if it's defined, if you have defined points, it is just the biggest y value and the smallest y value. All right, so let's see what else we have on here with our other two pictures, or other two graphs, I mean. Okay, so let me scroll, if I can. There it is. Okay, so just scrolling. There we go. Okay, so on these we have two different sets of intervals. On this one, it's half open or half closed. One side's closed, one side's open. And what we could do is still sketch it. If I do plug 1 into that function, I would get a y-coordinate of 3, and it would have a solid dot on it because of the closed interval on the 1. And then at 2, we already know where that is, but it's a parenthesis, so we're going to have an open dot like that. And then from there, I can connect it something like that. Okay, and so this time around I have at my peak, or not really at the peak, just it is the highest coordinate. My highest y-coordinate is 3, so that means I do have an absolute max there. Absolute max is 3 at x equals 1. This open dot, so that's not defined. So the parenthesis makes it so it's not defined. So we can kind of see it's the coordinate 2, 0. But that's not defined. So that means my y value that looks like it should be the smallest as 0 is not. Okay, it's just getting really, really close to 0. Okay, so that means I don't really have an absolute minimum. So no absolute minimum on this problem. Because where my smallest y-coordinate should be is not defined. So no absolute minimum. Smallest y is undefined. Okay, so that just shows, all right, so if you have a large y value that is defined, you could still have an absolute max. If you have an undefined, well, it's not gonna happen. Okay, one more here. So on 0, 2. So on 0, 2, I have my vertex of the parabola. So when I plug x equals 0 in, I get that point, and at 2, they're both open. So here I'd have open dots on those points. Well, neither of these are defined, so that means I have no absolute extrema. Okay, so they're both where my largest y value is undefined, where my smallest y value is also undefined. So that means these don't exist. Okay, so anyway, so this is how we deal with them when we have graphs. I'm going to quit now. Let's quit now, and we'll work on a different video where we are given functions, and we'll walk through our process. Okay, so thanks for watching this. If you have questions, please let me know. Otherwise, I will see you next time.